Hey guys, so we're going to have a look this lesson at some past paper projectile motions, so just some harder ones now. I'm still looking at the way we do projectile motion without vectors first. So this is classed as the old syllabus, but it's still relevant. Next lesson we'll start looking at now how we apply vectors. This particular first question we're going to look at was in 2015's HSC. It was question 14, which is the last question in the paper, so we're going to expect it to be pretty tough. So let's have a look. If you want to pause the video and give this a go, otherwise I'm going to jump straight into it and talk through how we would approach it. Alright, so we've got our projectile, and they've said that we have these two formulas here and that we don't have to prove them, which is great, because if they didn't say do not prove this, we would have to go through what we know our proofs from our last video and prove these before we would have to use them. But we don't have to do that. So question 1 says we need to show the horizontal range of the projectile is given as this. Okay. The first thing I'm thinking about is there's no t in this formula here. That's a big one. So I'm thinking somewhere along the lines to find this, I'm going to rearrange some equation to get t equals and substitute it in to eliminate t. But that's just my thought process whenever I'm showing something. Let's think now, horizontal range. That is literally this distance here, which is the x-intercept, isn't it? Technically this projectile, it has our two x-intercepts, so if we find these x-intercepts, we know that one answer is going to be 0, and the second answer is going to give us that horizontal distance. So let's think to ourselves, how do we find an x-intercept? Well, we make y 0. And these are all things that I would show the marker. So once I take my equation that has y in it and I solve that equal to 0, I'm going to solve this for t. Once I solve it for t, I'm going to get t equals some values, and I'm going to plug that into my horizontal motion formula, and then that will tell me the x value. Okay. Alternatively, I could find the Cartesian equation using both those equations they gave me, and once I have my Cartesian equation, solve that equal to 0 and I'd get the x value straight away. But I'm going to start by doing it this way. It's just, for me, the more logical way to start. So now if I have to solve this equal to 0, the first thing I'm going to do is factorize out a t. Minus a half gt. Now, okay, now we can see here, alright, well t is equal to 0, and t is equal to, well, I'm going to have to actually do a bit of work here. V sine theta minus a half gt equals 0. So let's go gt equals 2v sine theta. So t equals 2v sine theta on g. So they're the two times, okay, where y equals 0. But we don't want what time, we want to know what the x value is when that is occurring. But if we now know what time, we know it's not the 0 one because that's in our origin. We want the other value, the other time. So now we just take this t value and plug it into our horizontal motion formula, and hopefully we get what we need to prove. Okay, so doing that, I'm going to get, therefore, x equals v lots of the t value we got, cos theta, and cleaning this up a little bit, and so now this is the point where I start looking at what I need to show. I keep looking back up to the question. I'm very close. The next thing is, though, is just using a trig identity. Remember this trig identity, that's our double angle. So using that, I can see now how they've got the sine 2 theta, and the sine 2 theta was a giveaway for the double angle formula, so that's how I would write that identity out, show the marker you know it, and now make that substitution, which will just leave me with x equals, well, here's the 2 and the sine theta cos theta, which is what I know is equal to sine 2 theta. So I get an answer of v squared sine 2 theta all on g, which is exactly what I had to prove. End of proof. Okay, not too bad so far. Alright, now it says the projectile is fired at our angle pi on 3. Find the angle that the projectile makes with the horizontal at that time. Okay, so part 2, we need to find the angle at that time. So the first thing I'm going to think about is, okay, well, I want to find, if this is the velocity, this angle here. Think about, okay, if I need to find that angle, well, I need some other sides of my triangle. And then I could do sine, cos, or tan, SOHCAHTOA. So let's think about the other sides of the triangle. Well, we know that x is equal to vt cos theta. So if I'm going to do the horizontal edge here, because we're talking about velocity, I need to differentiate this, which just drops off with respect to t, so it just drops off the t. So v cos theta is my derivative. So that side length there, if we're talking about velocity, is v cos theta. So now if I do the exact same thing for y equals vt sine theta minus a half gt squared, y dashed, well, drop the t off, v sine theta. Alright, times the 2 out the front. Well, this one works out nicely. So then I get my y value for the velocity. Okay, so now I've got some sides labelled. I think, well, I could just do tan theta opposite over adjacent. Well, v sine theta minus gt over v cos theta. Alright, now they told me that the angle of the projection was pi on 3. Okay, so I can sub in my theta is pi on 3. And the other thing I can sub in is the time, because we need to know the angle at that certain time. Okay, so thinking about my pi on 3 is, that's pi on 6, this is pi on 3. Okay, so if I fill it in, time was 2v on root 3g all over, so now I just need to clean this up. Sine of pi on 3 is opposite hypotenuse root 3 on 2 minusing g times in by, let's see, my g's will cancel there. V cos of pi on 3, that's nicer. Okay, gives me root 3v on 2 minusing 2v on root 3. Now it's dividing by v on 2, which is the same thing as timesing by 2 on v. And that's that whole thing timesing. If I clean it up again, I get, do my cross swords, butterfly method. Well, this is looking nice. So hopefully you're following along there. Just some algebraic manipulation there. And 3v minus 4v gives me 1v on 2 root 3 timesing by 2 on v. My v's will cancel, my 2's will cancel, which gives me 1 on root 3. Well, that's very nice. Okay, but remember, that's what tan theta equals. So therefore, tan theta equals 1 on root 3, which gives me an answer that theta will equal pi on 6. And I just realized 3v minus 4v is negative 1v, which will give me a negative 1 on root 3. So then my angle won't be pi on 6, because if I think about my ASTC, negative 1 on root 3, so you just got to think about in here where tan is going to be negative. So we know that our subtended angle was still going to be our pi on 6, but it's the first pi on 6 we get with the horizontal is in here, and that makes sense that it's negative because I'm in the sine quadrant, which then gives me an angle of pi minus pi on 6, which is 5 pi on 6. So that is the angle at that time. There's a lot of work there, but we got there in the end. Okay, so for part 3, state whether the projectile is travelling upwards or downwards when that time is occurring. So think about what might prove whether it's upwards or downwards. So basically, we want to know if it's on its way up or if it's on its way back down at this particular time. Now, the most obvious way I can think of, and there could be more than one, but if I just find the vertical velocity at that time, if it's positive, it means it's going up. If it's negative, it will mean it's going down. So if I find the vertical velocity at that time, that's going to tell me positive or negative answer what it's doing. So, which means all I need to do is substitute in that time for into my vertical velocity, which I said was v sine theta minus gt. Okay, so there I have just gone through. I subbed in our angle because that was the angle we found in the previous question that the projectile had at that time. I then subbed in the time as well. Cleaning things up, I end up getting this down here. And looking at that, I went, oh god, this isn't helping me much. But when you really think about it is, and you can put it in your calculator, you're going to get a negative answer because square root of 3 is definitely less than 4. So when you subtract 4, I'm going to get a negative value. Whatever v is doesn't matter because I have a negative timesing by it. So that tells you that the gradient is negative, which means that it's going downhill, which answers the question. Now, the other way you can check this is if you turn your 5 pi on 6, that was the angle we got earlier, that projectile is at. If I turn that into degrees, I get an answer of 150 degrees. And just because I find degrees more understandable in terms of in reality, let's think about 150 degrees. If an angle is 150 degrees, it must be an obtuse angle. So the angle is 150 degrees, as I was saying. So think about that on the picture. It means it must be coming down. Okay, so without doing all that work that I did just do, you can simply tell the marker that you know the angle is obtuse, and therefore it will be going downwards. But either way is perfectly fine. Okay, shall we do another one? Well, what I might do is I'll send you guys a bunch of other questions similar to this that you can practice on your own with the work solutions. And what you can do is, if you're not sure about something in the work solutions, make sure you let me know in an email and I can send back a video explaining the situation, the concept. So I'll attach those questions to this when I post it for you.